There is a secret about the universe that Neil deGrasse Tyson can't stop mentioning in his lectures and interviews, something that he himself admits that when he first discovered it, he had to sit and process for hours because the implication is absolutely disturbing. We are talking about a discovery that not only questions everything we thought we knew about the cosmos, but suggests a fate for the universe so bizarre that it seems like science fiction, except that it is real science, based on meticulous observations and impeccable mathematics. And the most unsettling thing is that the more scientists investigate this mystery, the stranger it becomes. Tyson often begins his explanations of this by asking a simple question that should have an obvious answer but doesn't. He asks, if you throw a ball up, what happens? Obviously it goes up, slows down due to gravity, and eventually falls back down, right? That's basic physics we learned in school. Gravity pulls everything back up. So now imagine the entire universe as that ball. The Big Bang was like the initial throw. All matter and energy was thrown out in a colossal explosion approximately 13 years ago. 0.8 billion years, and since then the universe has been expanding. But here's the part that makes intuitive sense. Just as the ball slows down as it goes up, the expansion of the universe should be slowing down because all the matter in the cosmos is gravitationally pulling on all other matter, making the expansion slow down, eventually maybe even stopping and reversing in a big crunch, where everything collapses back. That was the logical expectation, the prediction that cosmologists had. And if you're one of those people who loves it when the science turns our expectations upside down and reveals that the universe is even stranger than we imagined, subscribe to the channel, because what I'm about to reveal now is just the beginning of a journey through the most disturbing discovery in modern cosmology. So in 1998, two independent groups of astronomers were studying type Ia supernovae, which are incredibly bright stellar explosions and, crucially, have a very predictable intrinsic brightness, which makes them perfect standard candles to measure cosmic distances. These scientists wanted to determine exactly how fast the universe was slowing down its expansion. They were hoping to confirm that yes, gravity is gradually slowing everything down. But when they analyzed the data on distant supernova, they found something that left them completely stumped. The supernovas were fainter than they should have been, not by much, but enough to be statistically significant. And weaker supernovae mean they are further away than expected, which means the universe is not just expanding. It is expanding faster now than it was in the past. Think about this for a moment. It's as if you threw the ball up in the air, and instead of slowing down, it starts to accelerate away from you, gaining speed as it goes up. This completely violates our intuition about how gravity works. Tyson describes the moment the scientific community received this news as one of the biggest shocks in modern physics. It literally rewrote our understanding of the cosmos. Because if the universe is expanding faster and faster, that means there is some mysterious force or energy that is pushing everything towards far away. A kind of anti-gravity. And this force is so powerful that it completely overcomes the gravitational pull of all matter in the universe. Scientists needed a name for this unknown entity, so they called it dark energy. Although Tyson is always keen to emphasize that this name is terribly misleading. It is not dark in the sense of being made of dark matter, and we don't know if it is actually energy in the conventional sense. It is just a marker for our colossal ignorance, a fancy name to say we have no idea what it is. And here's what makes it all the more disconcertingly. When cosmologists calculated how much dark energy would be needed to explain the observed acceleration, they came up with a shocking number. About 68% of the entire energy content of the universe is dark energy. 27% is dark matter, which we also don't fully understand. And only 5% is the normal matter that makes up stars, planets, you, me, everything we can see and touch. Tyson loves to put this into perspective by saying that we intelligent humans who build space telescopes and space accelerators particles, we only truly understand 5% of the universe. The other 95% are made up of things that we can't even detect directly. We only infer their existence from the effects they cause. It's like trying to understand a movie if you can only see 5% of the screen. Imagine the scientific humility it takes to admit that we are fundamentally lost about the basic makeup of the cosmos. But here's where the story gets really fascinating, because the discovery of dark energy not only showed us our ignorance, it opened doors to possibilities about the fate of the universe that are simultaneously wondrous and terrifying. To really understand why this discovery is so revolutionary and what Neil deGrasse Tyson means when he says it could change everything, we first need to delve into the story of how we came to understand that the universe is expanding, because this is a scientific journey full of unexpected twists and turns that began just over a century ago. In 1929, an astronomer named Edwin Hubble was using the 100-inch telescope on Mount Wilson in California. At the time, the largest telescope in the world, and he was studying distant galaxies, or spiral nebulae as they were called then, because many astronomers still debated whether these diffuse structures were within our Milky Way or were separate island universes. Hubble observed something extraordinary. When he analyzed the light from these galaxies through spectroscopy, he discovered that almost all of them showed a red shift. This means that the characteristic spectral lines of elements, such as hydrogen, were shifted to longer wavelengths, towards the red end of the spectrum, and by the physics of the Doppler effect. That's all. It could mean one thing: these galaxies were moving away from us, but Hubble's real insight was noticing a pattern. The further away the galaxy, the faster it was moving away. There was a direct linear relationship between distance and speed of recession. This relationship became known as Hubble's law, and the implication was inescapable. The entire universe is expanding. Space itself is stretching, carrying the galaxies with it like raisins in a loaf of bread that is rising in the oven. Tyson loves to use this raisin bread analogy because perfectly illustrates a crucial point. No galaxy is at the center of the expansion, just as no raisin is at the center of bread. From any point you look at it, all the other galaxies appear to be moving away from you. And the further away they are, the faster they move away. Not because they are moving through space, but because the space between them itself is expanding. Now, this Hubble discovery had a profound logical consequence. If the universe is expanding today, it means that in the past it was smaller, denser, hotter, and if you go back in time long enough, there would come a moment when all the matter and energy of the universe was compressed into an infinitesimally small and incredibly dense and hot point. This was the birth of the Big Bang theory, proposed by the Belgian priest and physicist Georges Lemaitre, who called this initial state the primordial atom. The idea was so radical that it faced fierce resistance. The term Big Bang itself was coined sarcastically by the astronomer Fred Hoyle, who defended a steady-state model where the universe always existed in balance. But evidence has accumulated, especially the discovery of the cosmic microwave background radiation in 1965 by Arno Penzias and Robert Wilson. This radiation is literally the afterglow of the Big Bang. Now cooled to just 2.7 degrees Kelvin above absolute zero, permeating all of space, it is the most direct evidence we have that the universe had a hot and dense beginning. So, until the 1990s, the cosmological picture seemed relatively clear. The universe began with the Big Bang. It has been expanding ever since, and the gravity of matter is slowing down that expansion. The big question was whether there was enough matter to eventually stop and reverse the expansion, causing a big crunch, or whether the expansion would continue forever, but getting slower and slower. It was a matter of measuring the density of matter in the universe and determining whether it was above or below the critical density needed to close the universe. Cosmologists were confident that with better telescopes and more accurate observations, this question would be resolved. No one, absolutely no one, was prepared for what supernova observations would reveal. The discovery that shook the foundations of cosmology came from two independent projects: the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. And what makes this scientific story so fascinating is that both groups were competing to measure the same thing: the rate at which the universe is slowing down, using the same technique, observations of type Y, a supernova in distant galaxies, and both independently came to the same shocking conclusion. The universe is not slowing down, it is accelerating. Type I, a supernova, are perfect tools for this type of measurement because they are extraordinarily consistent astronomical events. They occur when a white dwarf, the dense core remnant of a star like the Sun, accumulates matter from a companion star until it reaches a critical mass limit called the Chandrasekhar limit, approximately 1.4 times the mass of the Sun. At that point, the pressure is so immense that it triggers a thermonuclear explosion, runaway explosion, that completely destroys the white dwarf. And because all of these explosions happen at essentially the same critical mass, they produce approximately the same amount of light, becoming standard cosmic candles. If you observe a type Ia supernova and it looks faint, you know it's far away. If it looks bright, it's relatively close. It's basic astronomy. But here's the clever trick. The light from these supernovae also shows redshift due to the expansion of the universe. And the greater the redshift, the further away in time the supernova is, you're seeing light that was emitted billions of years ago. So by comparing the apparent brightness with the redshift of many supernovae, you can map how the expansion rate of the universe has changed over cosmic time. That's exactly what Perlmutter, Schmidt, and Rees were doing, observing supernovae in galaxies so far away that their light took billions of years to reach us. And when they plotted the data, something was fundamentally wrong. The high redshift supernova, the ones that exploded billions of years ago, they were consistently weaker than they would have been if the universe were slowing down. About 25% weaker. Tyson describes the scientists' initial reaction as pure disbelief. They checked and rechecked their instruments, their analyses, their assumptions, looking for any error that could explain this anomaly. But the data was solid. The distant supernova were genuinely further away than theory allowed. The only possible explanation was that the universe was expanding slower in the past and accelerating its expansion since, so it was like discovering that gravity was working in reverse. So what could be causing this acceleration? That is the question that defines modern cosmology. And this is where dark energy comes in. Although it is crucial to understand that dark energy is not an explanation, it is a name for the problem. It is our way of saying that there is something in the universe causing space to expand faster and faster, and we have no idea what it is. There are a few theoretical possibilities that physicists are exploring. The first and simplest is that dark energy is actually the energy of empty space itself, an intrinsic property of the fabric of the cosmos. Einstein originally introduced something called the cosmological constant into his equations of general relativity, a kind of negative pressure inherent in space that would push the universe outwards. He abandoned this idea when Hubble discovered expansion, calling it his biggest mistake. But perhaps Einstein was right. After all, if dark energy is the cosmological constant, then every cubic meter of empty space contains a tiny but non-zero amount of energy. And as the universe expands and creates more space, it creates more of it. Energy, which in turn further accelerates expansion, is a feedback loop that never stops. Another possibility is that dark energy is not constant, but rather a dynamic field that permeates space. Similar to the Higgs field that gives mass to particles, physicists call this idea quintessence. And if true, the strength of dark energy could be changing over cosmic time, which would open up a whole new range of possibilities for the fate of the universe. And I wonder, where are you watching from? Now, which continent, which country, which city? Comment on your location, because it is absolutely fascinating to think that in all these different places around planet Earth, people are contemplating together this same cosmic mystery that unites us as a curious species trying to decipher our own existence in this increasingly enigmatic universe. Now there is even a third, even more radical possibility. Perhaps dark energy does not exist, and what we are misinterpreting as acceleration is actually evidence that our theory of gravity, Einstein's general relativity, is incomplete or incorrect in gigantic cosmological scales. Perhaps gravity behaves differently when you are dealing with distances of billions of light years. This idea, called modified gravity, or MOND, is controversial, and most cosmologists do not favor it because relativity generally passed all other tests with flying colors. But the possibility exists and is being investigated. What Neil deGrasse Tyson repeatedly emphasizes is that this fundamental ignorance is nothing to be ashamed of. It is the natural state of the frontier of science. It is how we were before we understood electromagnetism or quantum physics. We name phenomena that we do not understand. We develop mathematical models that predict their behavior even without understanding their essence. And gradually, through increasingly precise observations and increasingly refined theories, we arrive at a more deep, dark energy is exactly at that stage now. We know it exists because we see its effects. We can measure its influence, but we don't know what it fundamentally is. So what this acceleration driven by dark energy means for the future of the universe, this is the part that could truly change everything we know. Because depending on the exact nature of dark energy, the cosmos could face radically different fates, some wonderful, some downright terrifying. Let's start with the scenario that most cosmologists consider most likely if dark energy is indeed Einstein's cosmological constant. This future is called the Big Freeze, or heat death of the universe. In this scenario, dark energy continues to drive the accelerated expansion. Indefinitely, galaxies that are no longer gravitationally bound to our local group will move away faster and faster, eventually surpassing the speed of light relative to us, not because they are moving so fast through space, but because the space between us and them is expanding so quickly within approximately 150 billion years. The only thing visible in the night sky from any planet in the Milky Way will be our own galaxy, and a few neighboring galaxies that have merged with us gravitationally. Everything else will have disappeared beyond the horizon space, its lights never reaching us again. And this is just the beginning. Stars will continue to be born for another few trillion years as the residual gas in the galaxies collapses and ignites. But eventually, all the fuel will be consumed. The last star will flash its final light in perhaps 100 trillion years, and the universe will be plunged into complete darkness, except for the faint glow of brown dwarfs and black dwarfs, which are cooled stellar cores. Even these will eventually radiate all their residual heat, and on scales of unimaginable times, tenths to the 100th power of years, even black holes will evaporate through Hawking radiation, leaving nothing but a cold, empty vacuum expanding forever. Maximum entropy, heat death, the end of all structure and complexity. Tyson describes this scenario as deeply melancholic, but also strangely serene. The universe simply darkening and cooling until there is nothing left but emptiness. But there is a second scenario that is much more dramatic and disturbing, and this is the one that really exemplifies when Tyson says the discovery could change everything. If dark energy is not a constant, but rather a field that is getting stronger over time, if the acceleration is increasing, then the universe could be heading towards a catastrophic event called the Big Rip. Torn apart, Individual galaxies separated from each other by the accelerating expansion of space. Then, on shorter timescales, individual galaxies would be torn apart, stars ripped from their orbits and thrown into the void. Then star systems would be destroyed, planets ripped from their orbits around their parent stars. Eventually, in the final moments, perhaps just a few months before the final Big Rip, the planets themselves would be torn apart, the tidal forces of dark energy overcoming even electromagnetic bonds that hold molecules together. And in the last fractions of a second, atoms would be torn apart, atomic nuclei separated from their electrons, and finally protons and neutrons destroyed into their constituent quarks. The universe would end not in a cold whisper, but in a scream of total destruction, where literally everything is torn to the most fundamental level. Tyson admits that this scenario gives goosebumps. The idea that the very fabric of space can become so violently expansive that it destroys every atom that exists is cosmologically horrifying. But here's the fascinating thing. Current observations suggest that dark energy appears to be consistent with a cosmological constant, which would favor the Big Freeze scenario over the Big Rip. But although the margin of error still allows for the possibility that dark energy is slowly getting stronger, future observational projects like the Nancy Grace Roman Space Telescope and the Vera Rubin Observatory are being designed specifically to measure the nature of dark energy with unprecedented precision, observing millions of supernovae and mapping the large-scale structure of the universe in extraordinary detail. There is even a third, less discussed but equally intriguing scenario called the Big Bounce, where if dark energy eventually slows or reverses, the expansion could slow down again and even reverse, causing a big bounce. Crunch that will perhaps be followed by a new Big Bang, creating a cyclical universe that expands and contracts eternally. This idea is speculative and has theoretical problems, but it has not been completely ruled out. What all these possibilities reveal is something deeply humbling. We are living in a moment in cosmic history where the universe is in transition. Dark energy has only recently taken control of the expansion. For billions of years after the Big Bang, the gravity of matter dominated, and the expansion was slowing down. But about 5 billion years ago, the energy dark matter overtook matter, and acceleration began. We emerged at exactly this time of transition. If humanity had evolved a few billion years earlier or later, we would see a fundamentally different cosmos. The implications of this for questions about why we exist when we do are profound and not yet fully explored. Now let's dive into some even deeper implications and current scientific debates about dark energy that reveal just how revolutionary this discovery really is. Because it doesn't just affect our understanding of the cosmic future, it calls into question fundamental principles of physics that we thought were well established. Start with what physicists call the cosmological constant problem. If dark energy is really vacuum energy, the energy density of empty space, then we can theoretically calculate how much of this energy should exist using quantum mechanics. Quantum field theory calculations predict that quantum fluctuations in the vacuum should create an enormous amount of energy. But when we do the math and compare it to the dark energy we actually observe, there is an absurd discrepancy. The theoretical prediction is greater than the observed value by a factor of 10 raised to the 120th power. This is often cited as the worst prediction error in the history of theoretical physics. Imagine you calculate that an apple should weigh 10 followed by 120 zeros of kilograms when it actually weighs 200 grams. This discrepancy suggests that there is something fundamentally wrong with our understanding of mechanics, quantum, or gravity, or both. Tyson points out that this is exactly the kind of theoretical crisis that has historically led to scientific revolutions. When observations conflict so dramatically with theory, it usually means that new, deeper physics is waiting to be discovered. Think of how Mercury's orbit not matching Newtonian predictions eventually led Einstein to general relativity. or how black body radiation not making sense in classical physics led Planck to quantum mechanics, we are potentially on the threshold of a similar leap in understanding. Another profound issue is the problem of cosmic coincidence, why the energy density of matter and the density of dark energy are approximately the same magnitude precisely now in cosmic history, for billions of years after the Big Bang matter completely dominated. And if dark energy is a constant, it will eventually completely dominate as the universe expands and matter dilutes. But it turns out that we are living exactly in the transition period where both are comparable. This seems a suspicious coincidence. Some physicists argue that this may be evidence of the anthropic principle, the idea that we observe this particular universe with these particular parameters because if they were very different, we wouldn't be here to observe them. Perhaps in a multiverse, with infinite variations of physical constants. Only universes with dark energy approximately like ours allow the formation of complex structures such as galaxies, stars, planets, and life. It is a controversial idea that many scientists consider unscientific because it is not testable, but others argue that it may be the only explanation for certain apparent coincidences in the laws of physics. Tyson is generally skeptical about the anthropic principle, preferring to look for more physical explanations and testable, but admits that when you come across such stark coincidences, all possibilities must be on the table. There is now a massive scientific effort underway to make actorized dark energy more precisely, because the distinction between a true cosmological constant and a dynamic field of quintessence has observable consequences. If it is quintessence, the equation of state of dark energy, the relationship between its pressure and density will change over cosmic time, and this would leave subtle signatures in the pattern of the cosmic microwave background. The distribution of large-scale galaxies and the properties of distant supernovae, missions such as the European Space Agency's Euclid satellite launched in 2023 is mapping the geometry of the universe and the growth of cosmic structures to constrain models of dark energy. The Dark Energy Spectroscopic Instrument is measuring redshifts of tens of millions of galaxies to trace the history of expansion in unprecedented detail. These projects could tell us in the coming decades whether dark energy is truly constant or evolving, and that answer will literally determine the ultimate fate of the cosmos. There is also a fascinating connection between dark energy and black hole physics that Tyson loves explore. Some theoretical physicists, including Stephen Hawking before his death, speculated that perhaps the information falling into black holes somehow contributes to dark energy, or that the evaporation of black holes through Hawking radiation may be connected to accelerated expansion. These ideas are highly speculative and controversial, but they illustrate how dark energy connects with literally every area of fundamental physics. Do you have some questions about these concepts of dark energy and accelerated expansion? If you do, comment there, because the scientific community is also full of unanswered questions, and it is exactly that spirit of curiosity that drives the discovery. Another intriguing aspect is how dark energy affects the formation of structures in the universe. Without dark energy, gravity would have continued pulling matter to aggregate into larger and larger structures. But with acceleration, the formation of new large-scale structures has essentially stopped. Clusters of galaxies that have already formed remain gravitationally bound, but new clusters are not forming. The universe has crystallized its cosmic web structure of filaments and voids and is now just diluting. This freezing of structure formation has implications for the possible existence of life in future cosmic eras. Civilizations that emerge trillions of years from now in a universe dominated by dark energy will have a radically different view of the cosmos. They will see only their own galaxy or local cluster against a completely empty and dark sky. The evidence for the Big Bang, the cosmic microwave background, will have been stretched to wavelengths so long that it will be undetectable. the accelerated expansion will have driven every other galaxy beyond the observable horizon. Tyson speculates that astronomers of these future civilizations may conclude that the universe is just their galactic island surrounded by nothing. They would have no way of knowing about the wider cosmos that previously existed. This raises a disturbing philosophical question. What are we missing in our time? What cosmic structures or phenomena have already been carried beyond our observable horizon by expansion? What evidence of fundamental physics or cosmic events are now permanently inaccessible to us because they occurred too soon or too far away? We are living in a bubble of speed-limited knowledge, finite light, and the accelerating expansion of space. And with each passing day, this bubble is effectively shrinking as more of the universe disappears beyond reach. It is simultaneously inspiring and frightening to think that we are in a cosmic race to understand the universe before parts of it become forever unknowable. So now that we've explored the nature of dark energy and its implications, let's get back to the heart of what Neil deGrasse Tyson means when he says that this discovery could change everything we know about the universe. Because it's not just about the cosmic future or the nature of dark energy itself, it's about what this discovery reveals about the limits of human knowledge and the nature of scientific inquiry. Tyson often reflects on the fact that we are living in a golden age of cosmology. In recent decades, we have made discoveries that our ancestors could not have even imagined. We've measured the age of the universe with less than 1% accuracy, mapped the distribution of galaxies across billions of light-years, detected gravitational waves from black hole collisions, photographed the event horizon of a supermassive black hole, and discovered thousands of exoplanets, including some potentially habitable ones. But dark energy reminds us that the more we learn, the more we realize how vast it is, the territory of the unknown. It is like climbing a mountain expecting to see everything from the top, only to discover that it reveals even greater mountain ranges stretching as far as the eye can see. This scientific humility, this ability to confront our ignorance without despair, but with renewed enthusiasm, is perhaps the most important lesson of the discovery of dark energy. Tyson argues that the human tendency is to assume that we are close to understanding everything, that only a few details need to be filled in. But the history of science is a story of forced humility. Newton thought he had discovered the ultimate laws of motion and gravity. Einstein showed that it was just an approximation. Einstein thought that general relativity could explain everything about gravity and cosmology, quantum mechanics, and now dark energy have shown that reality is stranger. Each generation of scientists discovers that the universe is deeper, vaster, more surprising than the previous one suspected, and there is no reason to think that this trend will end with us. In fact, the existence of dark energy practically guarantees that we are missing huge pieces of the cosmic puzzle. Because if 95% of the universe is made up of entities that barely we begin to characterize, let alone understand, what other fundamental phenomena may be operating that we simply have not detected yet? This question leads to one of Tyson's most provocative speculations about dark energy and the future of physics. He suggests that perhaps dark energy is our first direct observational evidence that we live in something like a multiverse, or that there are extra dimensions of space beyond the three we experience. Some high-energy physics theories, like string theory, predict extra dimensions packed into tiny scales. Perhaps dark energy is a gravitational leak of these extra dimensions, or perhaps it is evidence that our universe is embedded in a larger dimensional space that we cannot directly perceive. These ideas are highly speculative and currently untestable, but they illustrate how dark energy has opened up conceptual space for radically new possibilities about the nature of reality. Now let me ask, if everything we explored together about dark energy, accelerated expansion, and cosmic destiny expanded your mind as much as it expanded mine when I first learned, leave that like subscribe to the channel, and activate the bell, because we have a lot more mysteries of the universe to explore. And this kind of science that challenges everything we thought we knew deserves to be shared with everyone who loves understanding how the cosmos really works. Returning to the central question, there is another profound aspect of this discovery that Tyson emphasizes. It fundamentally changed how we think about the cosmos and our place in it. Before dark energy, we already knew that we were insignificant on a cosmic scale, a small planet orbiting an average star in an ordinary galaxy among trillions. But at least we could understand the rules of the game. Gravity, electromagnetism, the laws of the physics we learned made sense of everything we observed. Now we discover that most of the energy content of the universe is something we don't understand, that we can't detect directly, that defies our most fundamental theories. It's like discovering that you're playing chess, but 95% of the pieces are invisible and follow rules you don't know. This revelation should make us simultaneously more humble and more determined. Humble because we recognize that our understanding is fragmentary and incomplete. Determined because the history of science shows what seemingly impenetrable mysteries can be solved with creativity, rigor, and perseverance. Before the 20th century, we had no idea what made the stars shine. Now we understand nuclear fusion in exquisite detail. Before quantum mechanics, the structure of matter was completely mysterious. Now we can manipulate individual atoms. There is no reason to think that dark energy will be permanently mysterious. Some brilliant scientist, perhaps not yet born, will have the insight that will connect the dots. And this solution will probably reveal an even deeper layer of reality that we have not yet even imagined. Tyson also likes to point out that dark energy has philosophical and even existential. It forces us to confront the temporality of knowledge. Everything we learn about the universe, we learn from light that has traveled to us. Light from stars and galaxies that may have taken billions of years to get here. We are always looking to the past. We never see the universe as it is now, but as it was. And with the accelerating expansion, more and more of the cosmos is being pushed permanently beyond our observational horizon. There is an inherent finitude to what we can know, not because of limitations of our technology or intelligence, but because of limitations imposed by the structure of space-time itself. That there are questions about the universe that may be in principle unanswerable because the evidence has been carried beyond our reach. This realization is both humbling and liberating. Humbling because it recognizes fundamental limits. Liberating because it focuses us on what we can know and on the intrinsic value of the search for understanding, even when we know that complete understanding may be impossible. As we come to the end of this journey through the most baffling discovery in modern cosmology, it is worth reflecting on what it really means when Neil deGrasse Tyson says that dark energy could change everything we know about the universe. It is not just about the specific facts we have discovered, that the universe is expanding faster and faster, that 95% of it is made up of mysterious entities, that the cosmos could end in dark, cold, or violent rupture. It is about something deeper. It is about recognizing that the universe still has the capacity to completely surprise us, that our journey of discovery is far from over, that each answer we find opens up 10 new, deeper questions. Dark energy symbolizes the spirit of science at its purest level, the willingness to confront the unknown without fear, to admit ignorance without shame, to seek truth even when it challenges our most basic intuitions. Tyson sees the discovery of dark energy as a gift to humanity, not in spite of its mysterious nature, but because of it, because it gives us something monumental to investigate, a problem that will require perhaps centuries of scientific work to fully solve. And in the process of solving it, we will almost certainly discover even more surprising things about the nature of reality. Think of the scientists of the future who will look back at this moment in history. They will see the beginning of the 21st century as the era in which humanity first discovered that the universe was even stranger and more wonderful than anyone had imagined. They will study the pioneering observations of Perlmutter, Schmidt, and Riess in the same way that we study the observations of Galileo or Maxwell's equations as pivotal moments in the evolution of human understanding, and perhaps even to this moment they will have solved the mystery of dark energy. They will have a complete quantum theory of gravity. They will understand what happened at the instant of the Big Bang and why. Perhaps they will even have discovered how to manipulate dark energy or travel between universes in a multiverse. Or perhaps they will face even deeper new mysteries that will make dark energy seem simple in comparison, because that is the nature of scientific knowledge. Every answer is also a new question. Every mountaintop view reveals even higher mountains. And while this never-ending journey might seem frustrating, Tyson argues that it is, in fact, deeply inspiring. It means that there will always be something new to discover. There will always be frontiers to explore. There will always be the possibility that the next observation will revolutionize everything we think we know. The discovery of dark energy teaches us that we should hold our models of the universe lightly, with appropriate epistemic humility. Because nature has repeatedly proven that it is more imaginative than us, stranger, more surprising, the laws of physics that we consider absolute today may tomorrow be recognized as approximations, special cases of deeper theories, and this is not the fault of science, but its greatest strength. The willingness to change our minds when faced with evidence, of abandoning cherished theories when they no longer fit the data, of embracing the unknown with curiosity rather than fear. So when you look up at the night sky now, knowing what you know about dark energy and accelerating expansion, what you see is not just a static panorama of stars. You are witnessing an unfolding cosmic drama, a wildly accelerating universe driven by invisible forces we have barely begun to understand. You are seeing the past because starlight took years or centuries or millions of years to reach its eyes. You are seeing a cosmos that was fundamentally different when that light was emitted. And you are contemplating a future where all of it may disappear beyond the horizon or be torn apart by energies beyond our current understanding. This cosmic perspective that science gives us is perhaps the greatest gift of the scientific enterprise, the ability to see ourselves in true context, not as the center of everything, but as participants in a much larger story. A story that began almost 14 billion years ago with the Big Bang and will continue for countless eons into the future. A story we are just beginning to read, and what an extraordinary privilege it is to live in an age where we have the intellectual and technological tools to do that reading, where we can send telescopes into space to capture light from galaxies at the cosmic dawn, where we can detect ripples in the very fabric of space-time, where we can calculate the fate of the universe billions of years in the future. Our ancestors looked up at the same sky and created myths and legends to explain what they saw. We look and see something even more wonderful, a tapestry of physics and chemistry and history, cosmic energy that is simultaneously understandable through reason and mathematics and deeply mysterious in its most fundamental details. Dark energy is our current reminder that we are in the middle of history, not the end, that mysteries remain, that wonders await discovery. And if you share this sense of wonder at the cosmos, if these revelations about dark energy and the fate of the universe make you want to learn more about the mysteries of physics and astronomy, then you are exactly the kind of person we want in this community of cosmic explorers. Have much more lies ahead, from black holes to quantum theory, from the beginning of the universe to the search for extraterrestrial life. And each topic is as fascinating and surprising as dark energy. So this is the ultimate message that Neil deGrasse Tyson wants to convey when he talks about how this discovery changes everything. It's not just about the specific content of what we've learned about dark energy. It's about the attitude we should have towards knowledge and the universe, an attitude of perpetual curiosity, intellectual humility, and tireless determination. The universe has shown us that it is stranger than we imagined, and it will probably continue to surprise us in ways we cannot even predict. Our task as a curious species is to keep asking questions, to keep building bigger telescopes and more sensitive detectors, to keep refining our theories and testing our hypotheses, to keep pushing the limits of the knowable. Because even if we never fully understand all the mysteries of the cosmos, the act of trying already makes us more than we were, already expands our vision, already connects us with something greater than ourselves. Dark energy may remain mysterious for decades or centuries, but every experiment we do to study it, each observation we record, each theory we develop, brings us a little closer to the truth. And in this gradual approach, in this persistent search for understanding, we find not only answers, but also purpose, meaning, and a deep connection with the universe that gave birth to us, and that will continue long after we are gone.